Okay, so we'll continue Solidity programming. So Solidity Programming 1 and 2, we'll go into some more advanced areas like storage slots. That's going to be fairly complicated, and then briefly talk about proxy patterns. And then we'll go through some demos around dev environments. And then if there's time, I will show you how to solve the first Ethernet challenge. But before we dive in, any questions from last time or any questions around the assignment? Okay. All right, so let's see here. Storage slots. So storage slots is essentially the location where contract state variables are being stored. And each storage slot is of size 32 bytes, and it essentially starts at 0. So if you define, 3 variables, first one is storage slot 0, second one 1, and then the third one is 2. And there's 2 to the power of 256 storage slots available, which is more atoms than in the universe. And so the way to think about it is essentially a gigantic hash table that then, of course, is unique to that particular contract. So there's a ton of storage slots available. So here we have an example. So we have the contract storage layout. It has a public uint 256, which is 32 bytes, called ID, with a value of 543. And so if you start looking at storage slots using the Web3 library, so W3 ETH storage at, and you pass in the contract address and then the storage slot, you essentially get that value back in hex. 21F is 543. Would that work if the variable is private? Yes, exactly. Okay, so now 32 bytes is a lot of storage if you're storing smaller values. And so what the compiler and the EVMs are doing, they're actually packing values together. And so let's assume you have this situation right here. You have a 4 uint 64 and then 1 uint 256. It will actually pack those values into the same storage slot. And it starts from the right.
And the storage slot, so just to make sure I understand correct, so storage, every contract has storage slots equal to the number of atoms in the universe.
That's right.
Okay. Which every contract is also equal to every number of atoms in the universe as well. So there's a lot of storage slots. And so every contract starts at 0. And if I just went and added up all of the sizes of the variables for that entire contract, I would basically get an idea of how many slots they're actually using.
That's correct for simple variables. It gets more complicated once you start dealing with arrays and mappings, which are essentially dictionaries.
Okay.
Because that, of course, is dynamic.
And that multiple storage slots.
That's right.
Okay.
So as you see here, variable 1 is all the way to the right, variable 2 or value 2, then further to the left. And then value 5, it's a uint 256, that's going to be in storage slot 1. So the order matters. So what happens if you swap out value 5 with value 3 in the definition? Yes, that's right. So basically value 1, value 2 would be in slot 0, value 5 in slot 1, and then value 3 and 4 in slot 2. Okay, so storage slot array. So it starts to get a little bit more complicated. Because arrays are dynamic, right? You can always add values. And so the way it works is you take the ketchak hash of the storage slot. So in this particular case, the array is at storage slot 0, right? And that essentially gives you, in that gigantic hash map, it gives you kind of the starting point on where the array is located. And then you add the element index to access the specific element. So you take the hash, so note it ends in 563. If you're interested in the first element, so like element number 1.
So
like
one would be at 563.
That's right.
And 2 would be at 564.
Exactly.
And the use of the hash is to randomly place this in the continuum of available slots, and the hash gives you a low chance of a collision, so that's a safe operation.
Reasonably safe, yeah.
How do you know the size of
You don't. I don't think that is available from the outside. Obviously, in the contract, you can always say, hey, what's the length of values, right? Or the size. I don't exactly remember what the function is, but you're able to do it within the contract but from outside, you don't. But the way it would essentially appear. So one thing to keep in mind, right? You have an infinite array, right? Of possible locations in the storage slot array. And we're basically placing this value array here. And so what you would see is essentially the values of the array, and then the slots will be 0. Now, it's going to be difficult to differentiate, hey, is it actually storing 0, or is it just an empty storage slot? And then there's this last one. So this is around mapping. So let me just kind of jump into Etherscan real quick. So we know that if you're dealing with ERC20 tokens, there is a balance off, right? So here, for instance, we have the DOLA ERC20 token. And if I transfer tokens from my address to Priya's address, then essentially the value in the mapping, let me just bring up a ERC20 contract so you see what I'm talking about. So here we have the DOLA contract, right? And so we can read the contract, and there is the balance off, right? Where you input an address, and then it gives you the balance of the DOLA token for that particular address. And the way that is implemented is there's essentially this mapping, which is just a hash, like a dictionary that maps the address to the balance of each individual address, right? And so if I transfer, let's assume I have $1,000 tokens, and so then that means my address is listed with 1,000 dollar tokens as an entry in that hash, in that mapping. So if I now transfer 1,000 from my address to Priya's address, right? Then that value would be changed, right? And that's the state change that is happening when I transfer tokens to another account. Make sense? So then if we go to Etherscan, actually, oops. Let me take this transaction here, just a second. Okay, so if we use Falcon and we go into the so basically this view shows us how the token values have changed, right? So $and is essentially an address, and here it says it has 10 million less tokens now than compared to the previous transaction. And then here, this particular, it's a curve finance pool, has now 10 million more, right? So if these are the only dollar changes, right? So this is very readable, right? We basically see the address and the value. But if you go on Etherscan, you see these entries. You basically see a set of storage addresses, and then down here. Okay, so this one is essentially the value, and let's for fun just let's see whether that all matches up. Yeah, 10 million, right? It's all in way, right? So now we would have to put a decimal point somewhere. So here is essentially what it shows is that some value before was 10 million and now it's 0. And then here we see some value and it is increasing, right? 2.5 to 2D, right? Oh, okay. X calculator. So yeah, so it's increasing, but you have from this view, you have no idea what address it was transferred from. And so what you need to be able to do is essentially map an address to the storage slot where the balance is stored in the contract, right? So basically, let's go back to the contract. Here we have the mapping, right? And I want to find essentially the mapping of some address to this particular balance value. Okay. And Etherscan does not do that very nicely. Falcon kind of converts everything for you, which is great. So let's see how this works. So basically, here we have a simple storage layout contract with this mapping address uint, very similar to how the ERC 20 contract works. And then we just kind of hard code a few values, right? So this this address has so many tokens, this address, so many tokens, etc., right? Okay, so now in order to get that value, you calculate the cat jack of the concatenated padded value and the padded storage slot. So the storage slot is 0. And the value that you want to look up is, let's say, the first address, right? So we pad everything with zeros to the left, right? Same with the storage slot, which is the storage slot of the balance mapping. And that gives us a hash. And then we get the storage slot for that contract at that hash, and that will essentially return 678.
You're calculating just those two strings into a single string. You have two.
That's why it's 64, because we just concatenate, we don't add. And the other thing to keep in mind is that it has to be padded, right? So we concatenate those two values, we calculate the hash, and this hash right here, this 86DF, is essentially this hash right here. And so this is like, especially like in the Ethernet challenges where you now have a mapping, right? That, contains some values that you're interested in. And so this is how you get to the storage slot and able to read it. Yes. I mean, yeah, that's true. And you can always, so that's the other thing that is neat about blockchain, right? You can, when you basically say a get storage at, you can specify the block that you're interested in. So you theoretically, if you take all the blocks and look at one particular address, you can see the entire balance history from block to block. Now it's going to be super expensive and slow, and you use rather Dune to do that. But I don't know whether I mentioned this, but I mean, one thing to keep in mind is when you use services like Dune or Luabase, and even Etherscan, you're trusting them that they have parsed this data correctly, right? And so there certainly could be instances where the data is incorrect, and you go to the blockchain and it gives you something else. And so the blockchain, of course, is the authoritative force. Collisions, and I would just refer you to the link here that explains that, and that kind of comes into play when you have inheritance. Okay, so then the other thing that I want to briefly talk about is proxy pattern. We already touched on this, but contracts are immutable, which makes upgrades and bug fixes impossible. And so what the industry has adopted is this proxy pattern to create upgradable smart contracts. And let me see whether I can find one real quick. See whether we can find a proxy real quick. Let's see. Curve contract. Okay, so this is not a proxy contract because what Etherscan does, it tells you when it's a proxy contract, and so if you see code read write, then it's not a proxy. Proxy contracts are so common. I would be surprised if I'm having a difficult time finding. Okay, so there's a proxy contract. You see essentially the read and the write don't really have any, well, the read. So this is essentially the functions of the proxy. So this guy, proxy contract. Exactly. And so this then basically says, hey, set the implementation to implementation 1 or implementation 1.1, right? And then the read as proxy and the write as proxy, you're really talking to the implementation.
And it actually tells you where the.
That's right. That's right. And so then also if you go to this address, right, this is the address that you would interact with because that's not going to change. The implementation will change. But if you go to Etherscan, then of course you will see, hey, has the implementation changed?
Is this probably basically always done?
Remix, and then we'll probably take a break. So Remix is an IDE, online IDE. As you open up Remix Ethereum.org, it will already give you a workspace, and if you create new contracts, they will continue to show up. So remember the Merkle tree example that I showed a few weeks ago? That is still in here. Now, there's no authentication. And I think it's just using, local cookies. And so don't think that whatever you put in here is permanently stored. So I definitely recommend that you back things up. Also, Remix, I wouldn't really classify as a full integrated development environment. It's great for educational purposes, but if you're really serious, then you should probably go with something like hard hat or Brownie. But it certainly is very convenient, and as you are working with Ethernet challenges, this is the tool that I would recommend if you have to create a smart contract. Okay, so here we have the simple smart contract. So it's a smart contract that has one number. Does anybody know the default visibility on this one? If it's not public, yes.
Watching, by default.
Yeah, although I mean they should have specified it, right? I mean that's probably something that a smart contract auditor would already flag. Hey, you're not explicit here. Then it has a store function and then a retrieve function. Note that the modifier here, or the keyword view, right? Meaning that you can read the value. You don't have to pay transaction costs. Whereas here, that is missing. So if you invoke that function, you have to pay transaction cost. So then in Remix, you can compile the contract, and then it will essentially output the two files that you would expect. So there's the ABI. So here's the ABI, right? Exactly what you would expect. The two functions that are defined, retrieve and store, and then it kind of defines the inputs and the outputs, and then the state mutability and the fact that it is a function. So if you want to interact with this contract, right, that's the ABI that you would import into your Web3, well, the Web3 contract object. And then also the bytecode. View is so actually here it kind of structures it a little bit differently. Here's the bytecodes, and it actually already kind of extracts the opcodes. So I'm just kind of looking through this here real quick. Okay. All right. Somebody tell me the function hash of retrieve. Can you see whether you can figure that one out? There we go. 2E64CEC1. So, Duke, you want to explain? And then you take the 4 bytes, the first 4 bytes, because the catch-hack, of course, is 32 bytes. Okay, anybody else want to create the function hash for store? Huh? Yep, and also then, of course, you have to take into account spaces, right? You don't want to have spaces because the hash, this hash and this hash are different.
Yeah.
And also interestingly, no return value. Because if you think about when you invoke a function, the function selector is really just based on the inputs in the function name, not on the return value. Like it doesn't know which one to call because it hasn't.
You don't know that. You don't know that predictably. You only know that after the fact.
Exactly. Did anybody calculate it? The first one was 2E64CEC1. that that's something I would not expect. Let me just make sure that I copied this. Yeah, it's even 256. That's right, and we got that right here. And so remember, that is the gigantic switch statement that I told you about. That is hard-coded in the contract, right? It basically takes the input data value, gets the first 4 bytes, and then matches that up. And then basically what happens here, it basically says if the value that's on the stack is equal, right? Then it will push this value onto the stack and then jump to that location. So the 3B is the location on where the retrieve function is implemented. And then if you look further back here, it does the same thing. And then it pushes 59 onto the stack, and that's where the store function is implemented. So that's kind of how the function selectors work. And we'll debug. We'll go through it here in a second. Okay, so you compile it. You get the 2 files. Now the 2 files are really just important if you ever want to interact with the contract. Well, the ABI is. The bytecode, not really important because Remix will do the deployment for you. Then this is a cool tab. So basically, this is kind of like a test tab, deploy tab. So you can deploy this particular contract that we just compiled onto a chain. Not a real chain. So you basically say it's basically just your local environment. And then over here, oops, oh, jeez. Okay. Over here, you then essentially see the transaction, right? So this is the deployment transaction, and now your contract is deployed. And then down here, you essentially see your deployed contract. Now, if you, yeah, let me try this. So see, there's the deploy contract at D91, but I could just deploy it again. And now it's at D8, right? So you kind of, particularly important as you kind of run into issues, right? And you want to change code, recompile it, and then deploy it. Yeah. And then basically what this allows you to do is interact with the contract. Now, what this particular tab does, it gives you an account with funded Ether. And if you want to act, so this was the deployer, right? So this 5B address was the one that deployed the contract. And now it has less Ether because it had to pay for transaction fees. Now let's assume your contract has an only owner modifier, right? And now you want to test it out with a different account, you can just take another account. So now it's we're acting as AB8. Then we can basically set the value, press store. That's it's a transaction. So now the value is stored, and then we can retrieve it, and it gives you the value. So it's a great quick way to interact with the contract. But what is much cooler here is the debug functionality. Because every transaction you can essentially debug. I don't know whether, okay. And so I basically reverse all the way to the beginning. And what you will see here, the push 80 and the push 40 are essentially the opcodes in the contract, right? So this is the code that is now getting executed. And then, sorry, my screen is maybe not that big, but then you can also observe the stack and the memory. And then here, for instance, you have the call data. So this is the input data that I specified when I press the store. That's right. So the 6057361D is the function hash. And then the A6F is the value that I specified. And so let's go really quick through the function selector. So it basically pushes some stuff onto the stack, does some manipulation. And then let's see here, call data source, I don't know. Okay, so then basically here shift, right? Okay. Sorry. Call stack. So here's the stack. So let's see how that changes. See whether I can move this a little bit. Can you still read this? Okay. All right. So then we continue. It does a shift right. And so now what we have on the stack is what? The function hash, which came from the input. And then basically I'm sorry? I didn't quite get that question. Yeah, so the dupe essentially duplicates the stack, right? And we don't need to go through every single opcode here, but basically now what it does, it pushes from the code of the contract the 2E64CEC1 onto the stack. And then basically it calls, are these two equal, right? And in this particular example, they're not equal, right? And so now it continues. That's right. And so now we're at the function that we're actually calling. So it pushes it, it assesses, is it equal? Then it pushes a 59, which is essentially the location of where the implementation starts. And then it will jump to that implementation, to that value. And that's essentially then where we are in the store function. You can also just hit run to the next breakpoint. Hang on, where is it? There. So now we're in the function store. You have num somewhere. The A6F is the value that's on the stack. And then essentially, as we step through this, there's some pushing and swapping, but then essentially it will call store. And that will then store that value in the storage slot. It's probably, the way it works is the stack value at the top of stack is the storage slot, and one level deep is the value.
So if you were trying to like understand like what an attacker did, is it reasonable to go grab like the bytecode of the contracts? Not the bytecode, but like go get the best version of the code you can get from like a decompile. Throw it in here and say, okay, I'm gonna find a transaction that I think is bad. Basically recreate that transaction in here and be able to step through and see like where did something really happen.
Question, because you don't have to do all of that. You can go to, here, let me just pull up a transaction. Where was it? Let's take this transaction. Pull that up in Hinderly, which is yet another tool for developers. And it has a debugger built in that essentially allows you to debug transactions that have been mined on chain. So here is the transaction, a whole bunch of state. Here's the call stack, the function stack, but then here's the debugger. And so you can set breakpoints, and step through this, right? And that allows you to debug attack transactions. But one thing to keep in mind is this tool will pull code from Etherscan for contracts, right? Because otherwise it wouldn't have the source code. And so you only get the source code for the victim contracts as opposed to the attacker contract, because the attacker contract, they're not going to upload the source code. So there's.
You can still reverse engineer the source code, like, because we were looking at the attacker for the curve thing. And there's a better way to get this data, but like one of my ideas is like, well, I should be able to go find the thing that matches what an approval should look like. It won't be called approval, it'll be called like some Keka cache with inputs that match the contract definition of an approval. But you could go find that and you could say, okay, well now I have the memory address, et cetera. I can kind of still use it. It's just not named well. So you could do that, but that's just like painful debugging, I guess. It's kind of like, it's like kernel debugging.
Yes.
Just memory address.
Yeah. And I mean, this tool makes it a little easier. I agree with you that you may be able to piece together some source code for the attacker contract. But if you think about like understanding an attacker contract, the attacker will invoke a series of legitimate functions for which you have the source code available. And so in a way, you are able to piece together the history of what the attacker contract does by what gets invoked on the victim contracts. And so Tenderly is an awesome tool. It also allows you to do local debugging, gas profiler, state changes, the events. So it gives you a lot of information, a great tool for developers as well as security researchers. Okay, let me show you one more thing in Vmix. So stop debugging. So expect that you will have to use the debugger quite a bit for the Ethernet challenges. Okay, so I deployed locally. Now you can also deploy on-chain. And basically the way you do that, probably the best way to do that is by using an injected provider, which essentially connects to your MetaMask. That's right. So I have MetaMask here. Let's make sure I'm on the right, so my developer account, I'm going to connect it. I'm on the Gurley testnet. And I have half an ETH. Oh, one thing. How much ETH do you guys have for your account? Because Gurley, yeah. Because I was trying to play the Ethernet challenge yesterday and 0.05 was not enough. So you may want to go back to the faucet and on repeated days and get a little bit more. Oh, does it? Did it give you? Yeah, so go to the faucet again. Let me know if you have problems. I work with a bunch of people that apparently have thousands. So yesterday I was begging around. I was like, hey, can somebody send me some ETH? Anyway, so get some more ETH. At least a half, I would say. Maybe I'm overestimating, but okay. So I'm connected to the Gurley network, and then basically I hit deploy. And so now what will happen? It essentially sends the deployment instruction to my MetaMask. And keep in mind that a deployment instruction is nothing more than sending a transaction to the 0 address with essentially the deployment instructions and the code of the smart contract. Let me confirm that. Now that goes off to the Gurley testnet. And then we can look at it on Etherscan. That's going to take probably a few seconds. And one thing to notice here, right? It does not calculate the contract address here yet because it's not mined. There we go. So now we have the contract. Now, one thing that I noticed is that Remix now starts to uploading the source code as well. So now automatically your contract gets verified, which wasn't a feature a few months ago. Now if we go to the contract, we see read, which is essentially retrieve, currently 0, and then write. I could now connect my wallet. Then I can interact with it essentially through Etherscan, and so I'll write to the contract using the store. Again, let's look at the data real quick. So MetaMask already kind of converts this because it has, I suppose, the code. I don't know why it's taking so long. But if you go to the hex, you see again the function selector here and then the value. That's the transaction that I'm signing. Now that will take a second to confirm. Which one did I sign it from? Oh, I used my Ethernet address. Let's look that one up real quick. We see here the transaction that it called stored. See the value, and now if we go to the contract, go to read, we see the value that we just stored. So again, as you're working on your Ethernet challenges, you will work on the Gurley testnet. There's going to be instances where you have to deploy a contract, and that is how you do it. Now, one thing at times, oh no, we'll talk about that after the break. I'll talk more